Let me show you how it works for our example that we got stuck on. So here's the idea. Look for u2 such that, let's see here, what were we? 3. So a minus 3I times u2 equals to u1. Where that was the... Why would I do that? Let me show you, before I actually find such a u2, let me show you why I want to do that. If I have this, if I multiply by a minus 3I on both sides, what do I get to say? What's a minus 3I times u1 equal to? Zero, right? By construction, it's eigenvector, so it's 0. So what this gives me is that a minus 3I squared times u2 is equal to 0. And yet, a minus 3I times u2 is not equal to 0, right? So this is the definition of u2 being generalized eigenvector of order 2 with eigenvalue lambda equals to 3. That's what this data right here is. So what? We have two options in my storytelling. The one is for me to finish telling you the so what. The other is for us to find u2 explicitly. Which should I do first? Choose your own adventure. Choose.
So what?
So what? Okay, fine. The so what. So the magic formula. So if we take e to the ta, right, times u2, first of all, is this a solution? What is e to the ta times u2? A matrix times a vector is a linear combination of the columns of the matrix. But this is a homogeneous differential equation. If that matrix, every column is a solution, the matrix times u2 is a linear combination of solutions. Therefore, it is once more a solution to our differential equation. But more than just that, it's something we can calculate, because it's specifically... Now, we have to make the magic work, so we don't choose any lambda, we choose 3. This holds for arbitrary lambda. It's just only nice for certain lambda. So for our matrix, we like 3. So we do e to the 3t. And then I've got I times u2 plus t times a minus 3I times u2 plus t squared over 2 a minus 3I squared times u2 plus da 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 da. Now, my point to you would be that we have so constructed u2 to make this term 0, right? And what happens to a minus 3I cubed acting on u2? It's also 0. In fact, it makes this series truncate is the thing. And all that we keep is this guy and this guy. But this guy, by the way, is just u1 by construction, right? Because I said so up here. I'm saying we can find them by doing that. And so consequently, we get e to the ta u2 is equal to e to the 3t times u2 plus t times u1. And that will be my x2 that we could not find last time. Well, this time. So what is u2? Let me actually finish this here and find the general solution. So what is a minus 3i? It's a minus 3i u2 equal to u1 is explicitly 0, 1, 0, 0, uv equal to 1, 0. This tells me what? This tells me v is equal to 1, and u is free, right? So what do you think we should do with u? We just want the u2 to be non-zero, right? You can make u whatever you want. What? You say pi? I thought you said I. I take your pi and I set it to 0. The reason I do that is then I have u2 is really nice and simple. It's 0, 1. That's the usual choice here. Now, so consequently, my solution, my general solution, is c1 e to the 3t. Where'd it go? Come on, where'd you go? 1, 0. Plus this stuff up here, right? C2 e to the 3t times 0, 1 plus t times 1, 0. And if you look at this for a little bit, you can see that the ability we had to add, to choose u other than 0 would just amount to, like if we chose u other than 0, what it would end up doing is it would have put something here, right? So like that, this is the u that we had over here. And if you think about what that is, it just really amounts to relabeling C1. You're adding another copy of the first solution into the second one or something like that. So that's why you can, there's an ambiguity there. Sorry to the grader, but these will have different looking answers if you choose different. There's some ambiguity. I mean, there's some ambiguity in what the solution looks like here. Because you can always add or subtract copies of the first solution from the second, and that'll change the way it looks. Something like that. Anyway, that's what we do. When we don't have enough eigenvectors, we go looking for generalized eigenvectors. So what was the other problem we got stuck on? Remember? Last class? It was 3 by 3, right? And wasn't it 3, 3, 3? It seems like all my examples are 3, aren't they? I think it was this. It was 3, 3, 3, 1, 1, 0, 0, 0, 0. This was my A, right? And we're trying to solve dx dt equal to ax. This is pretty much the nicest one of these kinds of problems. So this one gives us lambda 1 equal to lambda 2 equal to lambda 3 equal to 3, right? We get a 3-peated 3. So let me just cut to the chase here. A minus 3i, you can check me on this. A minus 3i times e1 is equal to 0. A minus 3i times e2 is equal to e1. And a minus 3i times e3 is equal to e2. Now, let me just elaborate. What is e1, e2? E1 is 1, 0, 0. E2 in this language is 0, 1, 0. E3, 0, 0, 1. Now, I think we worked out E1 last time, right? We actually looked at the equation, and we found E1 was the only eigenvector, right? See, what would this say? A minus 3i squared on E2 is what? I know, it's been a long day. Somebody throw me a bone. Let's see here. Ooh, I could put that in your homework. That one's fun. What's that? We do it right now. No, I was about the identity I had scribbled down there. But so can you guys tell me? If a minus 3i times e1 is 0, what's a minus 3i squared on e2? In other words, multiply both sides of this by a minus 3i. You hit a minus 3i and e1, 0, yes. And likewise, a minus 3i cubed on e3 happens to be 0. All right, and yet a minus 3i squared on e3 is not equal to 0. e3 is in fact a generalized eigenvector of order 3 with eigenvalue 3. e2, generalized eigenvector order 2, eigenvalue 3. So what I'm trying to get at here is we could let u1, 1, 0, 0, u2, 0, 1, 0, u3, 0, 0, 1, and we can use this u2, so like here, let me finish the thought here, x2 will be e to the 3t, well, more generically, e to the ta times u2. And let's see here, to work that out, that's e to the 3t times I u2 plus t times a minus 3i u2 plus 1/2 t squared a minus 3i u2, right? This is 0, and this, so we get what? E to the 3t, yeah, this is, again, so u2 plus t times u1, right? Now, more specifically, that's e to the 3t times 0, 1, 0 plus t times 1, 0, 0. And then x3, e to the ta times u3, we would calculate as e to the 3t times I u3 plus t times a minus 3i u3 plus t squared over 2 a minus 3i squared u3 plus stuff that's 0. So this is e to the 3t u3 plus t times u2. What happens to this here? Let me just do this separately. So like this is t squared over 2, right? A minus 3i. What happens when the first copy of a minus 3i hits u3? It just bumps us down to u2, right? But then this is t squared over 2 u1, right? So we get 1/2 t squared u1. In other words, explicitly here, e to the 3t 0, 0, 1 plus t times 0, 1, 0 plus 1/2 t squared times 1, 0, 0. So if we have a triple, if we have a 3 times repeated eigenvalue, all right, it can be that we just get one eigenvector and we need a generalized eigenvector of order 2 and also order 3, which then when we feed it to the magic formula makes terms like t e to the 3t and even t squared e to the 3t appear. But we don't always need that, right? When we have a repeated eigenvalue like we saw earlier today, it can be that the matrix has enough eigenvectors so that we can just use eigensolutions, right? So which happens in general depends on the matrix, and it's a complicated question of linear algebra, what actually happens. But this much is the case. Linear algebra guarantees the existence of these kinds of what are called chains of generalized eigenvectors. Here, the chain u3, u1, u2 rather, u1. This is a chain of generalized eigenvectors. It's the lambda equals to 3 eigenvector, generalized eigenvector chain of length 3. And basically what the theorem in linear algebra says is that you can always find like n linearly independent such vectors that are arranged in these chains. This is called a Jordan basis. And it takes a lot of work to actually prove that that exists, but in fact it does. And I'm not going to try to test you on the quirky nature of how to find a Jordan basis in general. I just want to make you aware of it so that you know how to use it for like nice 3x3 examples like this. So if you can understand the examples we've gone over in problems like it, you should be fine. There are more in my notes of a symbolic nature. I'll try to go over some of those next time. So I think that's all I have for today.